Welcome to Open Channel Flow. In this session, we move beyond closed conduit systems and explore the fascinating world of open channel flow. Unlike pipe flow, open channel flow involves a free surface exposed to atmospheric pressure. Think rivers, canals, and spillways. Understanding this type of flow is critical for civil and environmental engineers working on irrigation systems, stormwater drainage, and flood control. We'll start by distinguishing open channel flow from pressurized flow and discuss how gravity becomes the main driving force. We'll explore concepts like flow regimes, specific energy, critical depth, and the Froude number, a key parameter that tells us whether the flow is tranquil, critical, or rapid. This topic brings together theory and application with real-world relevance in infrastructure and water resource management. By the end of this module, you'll be equipped with analytical tools to model and solve practical problems involving open channels. Let's begin by defining what an open channel is and how it differs from a pipe. Once you grasp that, everything else will flow naturally, pun intended.
1. Define it clearly, classify it confidently. Let's begin with what makes open channel flow distinct. At its core, open channel flow is any fluid motion that has a free surface exposed to atmospheric pressure, unlike pipe flow, which is completely enclosed. Think of rivers, canals, and stormwater ditches. These flows are governed not by pressure differences, but by gravity. The slope of the channel and the weight of the fluid itself are the driving forces. Now, a subtle but important point. In open channel systems, the free surface coincides with the hydraulic grade line, also known as HGL. This means that wherever you see the surface of the water, that's where the energy level sits. No pressure head here, just elevation and velocity contributing to the flow's behavior. Understanding this distinction is crucial because it changes how we analyze, model, and design systems involving open channel flow. From here, we'll begin classifying these flows based on depth, time dependence, and geometry. A strong grasp of the definition sets the stage. Everything else we discuss, from critical flow to uniform profiles, builds on this simple idea. Gravity rules, pressure doesn't.
2. Understand flow by its speed. Meet the Froude number. To understand the behavior of open channel flow, we need a way to classify how water moves. That's where the Froude number comes in, denoted as FR. It compares the flow velocity to the speed of surface waves. Mathematically, FR is defined as V divided by the square root of G times Y, where V is the velocity of flow, G is the gravitational acceleration, and Y is the characteristic depth. This single ratio tells us everything about the regime the flow is in. If the Froude number is less than 1, the flow is subcritical. That means gravity dominates and the flow is smooth and slow. Information can travel upstream. If FR equals 1, the flow is critical, balancing between gravitational and inertial forces. This is an unstable state, often used as a design reference. When FR is greater than 1, the flow becomes supercritical. In this case, inertia takes over. Flow is fast and shallow, and disturbances can't travel upstream. The Froude number is to open channel flow what the Mach number is to compressible gas dynamics. It captures the essence of flow behavior in a single expression. So whenever you look at a river, a spillway, or a channel, ask, is it tranquil, balanced, or rapid? The answer lies in FR.
3. Flow types. Read the water's behavior. To analyze open channel systems effectively, we must recognize how flow behaves with respect to time and space. This brings us to the classification of flow types. Start with steady flow. This is the calm and predictable case. Flow depth and velocity do not change with time at any given cross-section. If you observe the water level at a point in the channel, it stays constant. It's the engineer's favorite scenario because it's easy to model. In contrast, unsteady flow introduces time dependence. Depth and velocity at a location change over time. Think of a dam release or flash flood. Conditions evolve rapidly and must be monitored continuously. Now consider uniform flow. Here, the channel is so consistent that both depth and velocity remain constant along its entire length. This only happens under very idealized conditions, such as a perfectly prismatic channel with steady inflow. But in reality, most flows are non-uniform or varied. These can be broken down further. Gradually varied flow, or GVF, changes depth slowly over a long distance. This is what you typically see in natural rivers adapting to terrain. Rapidly varied flow, or RVF, involves abrupt changes, like what happens during a hydraulic jump, when supercritical flow suddenly becomes subcritical. These classifications aren't just academic, they guide how we apply equations and design real systems. Once you know the type of flow, you know which assumptions to make and which models to trust. It's like choosing the right lens to understand the movement of water.
4. Simplify flow geometry with hydraulic radius. Let's talk about one of the most useful geometric parameters in open channel flow, the hydraulic radius. It might sound like a complex concept, but it's actually very intuitive. Hydraulic radius, denoted as RH, is simply the ratio of the cross-sectional area of flow, A sub A, to the wetted perimeter, P. Mathematically, that's RH equals A sub A divided by P. Why does this ratio matter? Because it gives us a measure of how efficiently a channel conveys flow. A larger hydraulic radius means less frictional contact between the water and the channel surface, resulting in less energy loss and higher flow efficiency. That's why engineers love to optimize it, especially in man-made channels. Wetted perimeter includes only the part of the boundary in direct contact with the flowing fluid, not the open surface. This makes RH very sensitive to the shape of the channel. For example, circular pipes flowing half full and wide rectangular channels will have very different hydraulic radii, even if their flow areas are the same. Hydraulic radius connects geometry to flow behavior. It's not just a formula, it's the foundation of empirical equations like Manning's and Shezzy's. So whenever you see RH, think of it as the bridge between the physical channel and the equations we use to predict flow. It condenses the messy reality of shape and friction into a single, powerful parameter.
5. Specific energy, a powerful tool for flow depth analysis. To truly understand how water behaves in an open channel, you need to know how much energy it carries. That's where specific energy comes in. It's the sum of pressure head and velocity head measured from the channel bottom, and it's defined as E sub s equals y plus v squared divided by 2g. Simple formula, powerful implications. The term y represents the depth of flow, which accounts for the pressure head due to the water's weight. The second term, v squared divided by 2g, is the velocity head, representing the kinetic energy per unit weight of fluid. Together, they make up the total mechanical energy per unit weight relative to the channel floor. Specific energy is key to understanding critical flow conditions. It helps us determine whether flow is subcritical or supercritical, and it even plays a central role in identifying the critical depth where E sub s reaches a minimum for a given discharge. This concept gives engineers a way to visualize how flow depth and velocity interact under gravity. For instance, if flow depth decreases, velocity must increase to conserve discharge, which increases kinetic energy. But that comes at a cost. Total specific energy may rise or fall depending on the trade-off.
In real-world applications, specific energy helps us design efficient channels, control structures, and understand phenomena like hydraulic jumps. So don't just memorize the formula. Understand the relationship it describes. It's a compact expression of how fluid depth and speed shape energy dynamics in open channel flow.
6. Uniform flow when everything stays the same. Uniform flow is the ideal case in open channel hydraulics. It's when the flow depth, velocity, and channel slope remain constant along the length of the channel. This means the gravitational driving force is perfectly balanced by the frictional resistance. No acceleration, no deceleration, just a steady glide forward. To describe velocity in uniform flow, we use empirical formulas. The Chezy equation comes first, expressing velocity as v equals c times the square root of SO times RH, where c is the Chezy coefficient, SO is the slope, and RH is the hydraulic radius. This formula links geometry, slope, and roughness into one simple square root relationship. But in most practical engineering designs, we use the Manning equation. It's more intuitive and easier to apply. Manning's formula is V0 equals A over N times RH to the 2/3 power times SO to the 1/2 power, where A is a unit-dependent constant and N is the Manning roughness coefficient. This coefficient captures how rough the channel boundary is, from smooth concrete to natural riverbeds. Here's the insight. If the hydraulic radius increases or the slope becomes steeper, velocity increases. But if the channel is rougher, velocity decreases. That's why choosing the correct N value is critical. Even a small change in roughness can significantly impact flow predictions. Uniform flow conditions are rare in nature, but extremely useful for channel design. They provide a baseline, a reference condition. Knowing how to apply these equations allows us to size canals, drains, and channels with confidence. This is where theory meets the drawing board.
7. Choose cross-sections that flow with efficiency. In open channel design, shape matters a lot. The most hydraulically efficient cross-section is the one that delivers the most flow with the least resistance, and that boils down to maximizing the hydraulic radius. R sub H equals A sub A divided by P. To achieve this, you want to minimize the wetted perimeter P for a given cross-sectional area A sub A. Let's start with the rectangular channel. Its optimal form appears when the flow depth, Y, equals half the width of the channel, B. That's when friction losses are minimized for a given flow rate, and the hydraulic radius is maximized. This condition gives you the best balance between area and perimeter in a rectangular shape. Now, for trapezoidal channels, which are more common in earthworks and irrigation ditches, the most efficient shape is a bit more geometrically elegant. When the side slopes form a 60-degree angle and the depth y is equal to square root of 3 divided by 2 times b, the channel achieves optimal flow efficiency. This shape reduces unnecessary contact between the water and the channel boundary, lowering energy loss. These aren't just geometric curiosities. They are practical design tools. They help engineers size channels that move water efficiently without overspending on materials or land. So when you hear best cross-section, think minimum perimeter, maximum hydraulic radius, and shapes that work with nature, not against it. 8. Gradually varied flow, reading the river's slow transitions. Not all changes in open channel flow are sudden. In fact, most natural flows adjust gently over long distances. That's what we call gradually varied flow, or GVF. In this regime, both depth and velocity change slowly with distance. To describe it, we use the GVF equation. dy dx equals S naught minus SF divided by 1 minus FR squared. This equation tells us how the water's surface profile evolves based on the bed slope, S naught, friction slope, SF, and the local Froude number. The shape of the water's surface, called the flow profile, depends heavily on the type of slope. For steep slopes, the normal depth yn is less than the critical depth yc, meaning the flow is swift and likely supercritical. For critical slopes, yn equals yc, and the flow rides a fine balance. Mild slopes, common in engineered channels, have yn greater than yc, indicating tranquil subcritical flow. Horizontal and adverse slopes introduce special cases. A horizontal slope means zero bed inclination. Think of a perfectly flat channel, while an adverse slope actually rises in the direction of flow, creating unusual and often unstable conditions. Understanding these profiles is crucial for designing weirs, spillways, and transitions. If you know the slope and the type of flow, you can predict how the water surface will respond. GVF helps you anticipate backwater curves, drawdown effects, and control structure performance. It's not just math, it's a map of how water adapts to terrain.
9. Rapidly varied flow, where water changes its mind fast. In open-channel hydraulics, not all transitions are smooth and slow. Sometimes the flow shifts dramatically within a short distance. That's rapidly varied flow, or RVF. One of the most important and visually striking examples is the hydraulic jump. You've likely seen it where fast-moving water suddenly rises and slows down, like downstream of a sluice gate or spillway. A hydraulic jump is nature's way of converting dangerous supercritical flow into a more stable subcritical one. It's not just a change in flow regime, it's also a powerful energy dissipation mechanism. The turbulent mixing in a hydraulic jump releases excess energy, protecting downstream structures from erosion and damage. The depth change across the jump isn't random. It follows a mathematical relationship. The ratio of post-jump depth, y2, to pre-jump depth, y1, is given by y2 divided by y1 equals 1/2 times -1 plus the square root of 1 plus 8 fr1 squared, where fr1 is the Froude number before the jump. This formula shows that the stronger the incoming supercritical flow, the more dramatic the jump. But it's not just about depths. Engineers also care about how much energy is lost. The energy dissipation ratio tells us how effective the jump is. H sub L divided by E sub 1 equals H sub L divided by Y1 plus V1 squared divided by 2G. A high dissipation ratio means a large amount of kinetic energy is being turned into turbulence and heat. Hydraulic jumps may look chaotic, but they're a predictable, controllable part of hydraulic design. Understanding them lets us harness their benefits and avoid their dangers. In short, RVF is where open-channel flow gets dramatic, and hydraulics becomes performance art.
10. Measure and control flow with precision and purpose. Controlling and measuring flow in open channels isn't just about observation, it's about precision engineering. Whether you're regulating floodwaters, managing irrigation, or designing lab flumes, you need tools that connect geometry to discharge. Enter sluice gates and weirs, two of the most widely used hydraulic control structures. Start with sluice gates. These are underflow devices, meaning water flows beneath the gate. The velocity of flow depends on how much the gate is opened and the upstream depth, y1. Two forms are common, one using a general discharge coefficient, CD, and the other introducing width B and opening height A through the equation V equals CA times B times A times the square root of 2G times Y1. These equations allow you to predict how much water will pass for a given gate configuration. Now consider weirs, which operate through overflow. A broad-crested weir spreads the flow over a flat crest. Its discharge depends heavily on the weir head H, with velocity given by V equals CWD broad times B times the square root of G times 2/3 to the power of 3/2 times H to the power of 3/2. It's a workhorse for measuring steady flow with minimal turbulence. Sharp-crested weirs offer more refined control. The rectangular type has a familiar form. V-rec equals CWD rec times 2/3 times B times the square root of 2G times H to the power of 3/2. The triangular or V-notch weir introduces angular geometry for precise low-flow measurement. Its formula, V equals CWD triangle times 8/15 times tangent of theta over 2 times the square root of 2G times H to the power of 5/2. The sharper the notch, the more sensitive it is to small changes in flow. These equations might look complex, but they're grounded in physical insight. You're not just plugging into formulas, you're applying principles of energy, pressure, and flow to create systems that are both functional and measurable. This is where open channel theory becomes practical engineering.
11. When flow gets complicated, special cases that matter. Let's shift from the textbook to the field. In real-world engineering, flow rarely behaves perfectly. That's why we need to study special cases and applications, because that's where safety, reliability, and performance are truly tested. Start with flow over bumps and weirs. It may look simple, but the physics depend entirely on the upstream Froude number. Supercritical and subcritical flows respond differently to obstructions. Whether the flow accelerates, decelerates, or forms standing waves depends on energy levels, not just the shape of the bump. So never underestimate a curve in the channel. It's a test of your understanding of flow regimes. Hydraulic jumps, often seen as chaotic, are actually intentional tools in water engineering. They are strategically used to dissipate energy, especially downstream of dams and spillways. The violent turbulence they produce helps protect downstream channels from erosion. In this context, turbulence is your friend, not your enemy. Then there's bridge scour, one of the most dangerous yet overlooked issues in hydraulic design. As water flows past bridge piers or abutments, vortices form and start removing sediment from the foundations. This process, known as scour, is the leading cause of bridge failures worldwide. It's not about average depth or slope anymore. It's about local velocity fields and vortex dynamics. In all these cases, open channel flow theory is still valid, but it needs to be applied with insight. Real-life applications demand more than equations. They require understanding of transitions, instabilities, and interaction between flow and structure. These are the scenarios where good engineers become great ones.